All right, so we're gonna we just defined increasing, decreasing functions. So now we're gonna define a theorem. And this is gonna be the sign of a derivative. So for this theorem, we're gonna let f be a differentiable function. On open interval a to b. Then we get two things. If the first derivative is greater than 0, so if the first derivative is positive, for all x that are elements of the open interval a to b, so if the first derivative is positive for everyone in an open interval, then the base function, or the function it came from, is increasing on that interval. So if you have an interval from a to b, and the first derivative is positive, then the function who you took the derivative of, they are increasing. And we get a similar statement if the first derivative is negative on an interval. Then the function that we took the derivative of is decreasing on that interval. Okay, so we're going to look at a few examples here, and then we'll move on. So, first example, this is actually example 2 from the book. What we want to do is we want to show that our expression f of x equals natural log of x. We want to show that that is increasing. So they didn't really specify what interval this is. So what we need to know a little bit of information about natural log of x. So we need to remember from like algebra 2 that the domain of natural log of x is 0 to infinity, which means natural log only exists for 0 to infinity. So it only exists for positive numbers. So first of all, we need to remember that. So what we want to do, we're going to find find f prime of x, and then we're going to check f prime of x's sign on 0 to infinity. So this is kind of the approach, this is the approach we want to do. So we want to find what's the first derivative, and once we get the first derivative, then we're going to check what's the first derivative sign on 0 to infinity, and hopefully we can show that the first derivative sign is positive, because then if the first derivative is positive for all x in 0 to infinity, then the basic function that we took the derivative of, in this case natural log of x, that will be increasing, and we'll have shown what we're trying to do. So f prime of x, remember the derivative of natural log of x is 1 over x. And then we'll say, well, 1 over x, if you input a positive x, 1 divided by a positive x is positive. So this is positive for all x in 0 to infinity. So by our theorem, so the first derivative is positive for all x in 0 to infinity. So by the theorem, f is increasing. Sorry, let's say it this way. F of x equals natural log of x is increasing on 0 to infinity. So basically, we wanted to show that the function f of x equals natural log of x is increasing. From our theorem, if the first derivative is positive for all x in an interval, then the function is increasing. So we said f of x is natural log of x. The domain of natural log of x is 0 to infinity. So what did we say? Well, we wanted to find what's the first derivative and then figure out what the first derivative sign on 0 to infinity is. First derivative is 1 over x. 1 over x is positive for all x in 0 to infinity. So then by the theorem, we get f of x equals natural log of x is increasing on 0 to infinity, which is where the function is defined. So that means it's just an increasing function. Everywhere it's defined, it's increasing. So let's look at example 3. Okay, so example 3 says find intervals on which f of x equals x squared minus 2x minus 3 is monotonic. And let's see. Not sure if we defined that word yet. I think we didn't define that. So we're going to define that real quick in here. We'll say definition of monotonic. So we say f of x is monotonic on an interval a to b if it is either increasing or decreasing on a to b. So this is our definition of monotonic. So what this means, what the question is asking us to do, the question is asking us to go through and figure out where f of x is increasing and decreasing. So we'll say, what does the question want? So what the question wants is, it wants us to find where f of x is increasing or decreasing. So the function is monotonic if it's increasing or decreasing on a region. So we basically want to figure out what are all the regions where f of x is increasing and what are all the regions where f of x is decreasing. We want to note whether f of x is increasing or decreasing on each region, and then those will be the regions where the function is monotonic. So let's go through and do that. Let's take the first derivative, which, so I'm using the theorem. I want to use the theorem. If I can get the first derivative, figure out where the first derivative is positive or negative, I can use this theorem up here to figure out where the function that we took the derivative of is increasing or decreasing. So the first derivative of x squared minus 2x minus 3, derivative of x squared is 2x, derivative of negative 2x is just negative 2, and the derivative of negative 3, that just goes to 0. So this is our first derivative. I'm going to set this equal to 0. And then when I solve that, I can tell where the function should change signs. And I'm going to build a little chart. So we'll say, basically the idea here, I can see that if I put 1 in, this the function is 0. The first derivative is 0 when x is 1. So what that means is this right here is a diagonal line, and at 1, we know there's an x-intercept at 1. The line either is doing something like this or it's doing something like this. So basically, I'm going to build a little chart here and say, okay, at 1, I'm going to break up the whole real number line at 1. Basically, if we have the number line here, here's a 1. I'm going to break up an interval like that and an interval like that. And I'm going to build a chart to kind of represent that. So here's 1. To the left of 1, we have negative infinity up to 1 interval. And then to the right of 1, we have 1 up to positive infinity. This is for, I'm going to keep track of what f prime is doing. At 1, f prime is 0, because we set the first derivative 0 to get the x value 1. And then at, for x is less than 1, see how I can put a 0 in for x. 2 times 0 is 0 minus 2. My first derivative will be negative for x is less than 1. And then if I input numbers bigger than 1, my first derivative is positive. Like if I input 3 over here, 2 times 3 is 6. 6 minus 2 is 4. So this right here is my chart. So I should note on the AP test, you can use these charts as kind of guidance, but when you refer back to them, you need to quote the theorem. So you can't just say chart here and jump directly to f decreasing on this and f increasing on that. You have to state a little bit further. So to kind of write this up like you would see on the AP test, we will say f is decreasing on negative infinity to 1, and we'll say as f prime of x is less than 0 on negative infinity up to 1. So rather than just saying it's decreasing because we have the chart there, we can use the chart to kind of help us, but we have to kind of fully state why is the function decreasing, what's indicating that the function's decreasing. Well, what's indicating the function's decreasing on that region is the first derivative is less than 0. And then for monotonic, you need to, where are you increasing and decreasing? We got the decreasing. Then we can say f is increasing on 1 to infinity as f prime of x is greater than 0 on, on 1 to infinity. And then this is where the function is monotonic. So it's decreasing on one region, it's increasing on the other, and we get our functions monotonic there. Okay. So we're going to move along. We got this first derivative test for critical points, the next theorem. We'll go ahead and write that out, and then we'll do one quick example, and then we'll save the rest of it for the next part. Actually, the bell's about to ring, so we'll stop this part here, and we'll get the rest of it here in a minute. So, for this chunk, we the second part, we focused mainly on this theorem here. Let f be a differentiable function on an open interval. If the first derivative is positive over an open interval, then the function that you took the derivative of is increasing. If the first derivative is negative, then the function you took the derivative of is decreasing. I guess I should note, if this information is about the second derivative, so if you had the second derivative is positive, then you could say the first derivative is increasing, and if the second derivative is negative, then the first derivative is decreasing. And you could keep upping the number of derivatives you have. So like if the third derivative is positive, then the second derivative is increasing. If the third derivative is negative, then the second derivative is decreasing. And that keeps going on and on and on. So if you have a region, kind of generalizing it, if you have a region where one derivative is positive over that open interval, then the previous derivative would be increasing there. So like if the 14th derivative was positive on an interval, then the 13th derivative would be increasing there. If like the, 103rd derivative was negative on an interval, So if the 103rd derivative was negative on an interval, then the 102nd derivative would be decreasing on the same interval. So we'll just say that this kind of wraps up part 2 here.